Organic chemistry. I hope you guys didn't wait too long. I was actually just comprising all these notes, and there's a lot with reductions, so as I state right here, I highly recommend you write this all down on your 4x6 card, because even I forget some of these rules sometimes, because there are so many, and they are so similar, but they're also so unique. And this is just kind of a meme to start you out with. When you react this molecule with H2PD, it reduces it to nothing more than atoms. Just like that. That's the product. But now we're actually going to look at some real chemistry, all jokes aside. So, the first mechanism, or reduction, BH3, it reduces aldehydes and ketones plus carboxylic acids, but it does not reduce esters or amides. So what do I mean by that? Well, if we react these with BH3, you'll get that with a ketone, that with an aldehyde, that with a carboxylic acid, and what are you doing in here, ester? Get out of here. Because once again, we can't react it with esters. Now, there is one special thing we can actually do with BH3. We can actually do an anti-Markovnikov addition. And what do I mean with that? When we react this molecule right here with BH3, you'll actually get something that looks like this, because it's a Markovnikov addition, which means it's going to go where there's, or an anti-Markovnikov addition, meaning it's going to go where it's less stable. So, and this also has to be in the presence of H2O and NaOH, but that's the only special thing with BH3. And actually, in one of my next videos, we're actually going to be doing a problem with this, and you'll see what I mean by that. But moving on to the next reduction, we have NABH4. It only reduces ketones and aldehydes. So, here's some examples. It will reduce this ketone into something that looks like this. We'll reduce this compound into something that looks like this. And once again, it does not reduce acid derivatives or amides. Only reduces ketones and aldehydes, and that is NABH4. Moving on. LAH, also known as, can't even pronounce that, Lehi? Let's just call it Lehi. I don't know actually what that stands for, but you might see it on the exam as LAHI. And it can reduce everything. Now, what do I mean by that? I literally mean it can reduce everything. So if you have a ring structure, it can do this, which means it breaks the ring. And since we also have the NH plus in here, we'd be given that. And we'd be given this, forming a diol. So that's one thing LAH can do. Now it can also reduce our ketone back into this once again. And once again, the blue arrows are actually just the same reagent. I just didn't want to have to rewrite LAH all the times. It can reduce our carboxylic acids into something that looks like this, and it can reduce our aldehydes into something that looks like this. And that is what LAH does. So, moving on. Dibol H, much like Diablo. It deprotonates acids, reduces esters to aldehydes, doesn't mess with our ketone and aldehyde brethren though. So, what do I mean by that? When we have Dibol H, it will reduce our ester into a ketone. Much like that. If we have a carboxylic acid, it reduces, actually it doesn't reduce, my bad. See, like I said, write this stuff down because it is kind of confusing. It deprotonates our acids. So you'd be given something that looks like that when you use Dibol H with a carboxylic acid or, an acid. So, our next reduction is PCC, and it sounds like a hardcore drug, but it's actually not. It is actually an organic chemistry mechanism / reaction. It makes ketones from secondary alcohols and makes aldehydes from our primary school alcohols. Oh my gosh, that is very loud. Okay, so with this tertiary or secondary alcohol, it will actually make a ketone, and with this primary alcohol, it will make an aldehyde. And that's what PCC does. Moving on, we're just flying on through these. H2PD, kind of like R2D2, but way less cool. It does a whole lot. It can reduce ketones to alcohol, gets rid of alkene and alkyne bonds, only affects aldehyde/ketones, does not affect esters or acids. However, the benzylic carbon position, as you could see from our first example, the joke example, is a unique position for H2PD because it can actually reduce the ketone if it is in that benzylic position. The benzylic position is right here when attached to a benzene ring. So it will actually get rid of that ketone and leave us something like this. Now, an overall just drawn out molecule that's not part of a benzene ring, it will do this. Gets rid of that alkene bond, gives us something that looks like this. Now, something else it can do that's unique is for this, forgot to draw that in, for this molecule right here, at the benzylic position, it will just get rid of the OH, leaving us with this product. Same thing with this product, with this right here. I know how I said it doesn't react with esters, but once again, the benzene ring is kind of a weird instance when it can react at that benzylic position, and all it does is completely get rid of the ester. I mean, the ester is still present in the solution, but for our exam and for our purposes, it just gets rid of it, much like that. And zinc/HCl does the exact same thing, but it doesn't affect alkenes and alkynes. So moving on, Camino 4, or chromatic acid. This once again does a whole lot, and it does different things when reacting with the benzene ring. This one's actually very complicated, and there's a whole lot of rules, so I highly suggest reading over your papers for this one, because there's a whole lot of things that I probably didn't even cover with this one. But the basics of this, the basics are, on a benzene ring, it basically just makes carboxylic acids at the benzylic position, unless it is a tertiary carbon. But if it's on a tertiary carbon, it makes carboxylic acids at that benzylic position. Once again, benzylic position is right here. Same thing with esters on a benzene ring. At the benzylic position, it will make a carboxylic acid. This molecule is actually called benzoic acid. Now, KMNO4 can also oxidize this molecule into something that looks like this. Now then, when we're looking at KMNO4 on an overall large molecule down here, first thing to do is locate tertiary carbons, or secondary carbons. Then locate your primary carbons. I'll label my primary carbons in red, my tertiary carbons in blue that are going to get oxidized, and my tertiary carbons I will highlight. So, primary carbons usually go to carboxylic acids. Secondary carbons will go to ketones, and our tertiary carbons are unaffected. So for this molecule right here, we have a ketone that forms. We'll have a carboxylic acid that forms there, and then at this tertiary carbon, nothing will happen. So once again, moving on to this molecule down here, same thing. As before, we're just mixing and matching. So you would get a product that looks like this. Pretty cool, I know. So let us move on. the final thing we're going to be doing is H2CrO4. It reacts the same as Camino, but it is a lot stronger. And what do I mean by that? Camino actually can't oxidize this, but H2CrO4 can, and it can also oxidize this. So it will actually give us something that looks like this right here. Now, H2CrO4 can also break rings. What do I mean by that? I mean it can actually break a ring and then oxidize it, so that we are then given, we count this out, 1, 2, 3, 4, and 5. One, two. Actually, let me count my carbons. 1, 2, 3, 4, and 5. 1, 2, 3, 4, and 5. And then at our 5th position, we will actually have. Oh, I drew this wrong. Oh, drew that wrong actually. Kind of complicated to draw this one out. So, product that looks like this. It breaks the ring and then it oxidizes it. And I know that's kind of complicated to visualize, and that's why I have to write this down, because this is a complicated ass reduction. 5, 1, 2, 3, 4, and then 5. And then the oxidants would then be added on. So, I hope this helped. Those are reductions, and those are all the reductions you're going to have to know for this exam. Go back through those notes and stuff, because there's not much I didn't leave out, but there's just some nitty-gritty details that might help you and better understand this stuff. But with that all being said, these are the basics to actually understand how reductions work. And if you write this down